Lab 4, Physics of Extreme Sports. The objective of this lab was to examine the motion of a spring mass system in which the mass swings in an arc while oscillating on the spring. Models. Some of the models that we used were an observed model through the video of an oscillating mass hanging by a string, and then we created a model by collecting the data points through the use of a tracker pointer program, and then we had a computational model which was initialized by the conditions observed from the observed model. Fundamental principles that we used in this lab. The first fundamental principle was Newton's second law. The final velocity equals final initial velocity plus the net force divided by mass times the change in time. Second fundamental principle was Hooke's law, or the spring force equals the negative spring constant times the length of the spring. Third principle was energy principle, or the change in energy equals the change in kinetic energy plus the change in potential energy from gravity and plus the change in potential energy from the spring. The next principle is the kinetic energy is 1/2 mv squared. Spring potential energy is 1/2 kss squared. And the gravitational potential energy is mgh. Some of the calculations that we used to find the spring constant k was that the period, or t, equals 2 pi times the square root of m divided by k. And from that we get that k is equal to 4 pi squared times m divided by 2, or divided by t squared. The next thing we calculated was the relaxed spring length, or L0, which since we know that at rest the force of the spring is equal to the force of gravity, and then we can have that be mg equals ks, or mg equals k times the vector L minus L0, and L0 equals the vector L minus mg divided by k. So our initial conditions were the mass of the object is 0.402 kilograms, the oscillation period is 1.52 seconds, the spring constant is 6.87 Newton per meter, and L0 equals 0.1265 meters, and L equals 0.7 meters. Here is the video of the object spinning around, oscillating around, and then here was the data collected from that graph. So we see that it is oscillating up and down along it on the y-axis, and then also on the x-axis. Here is my code for the glow script. Yep. So we change the ball's velocity, the ball's mass, and then further down I changed some of the constants, such as ks equals 6.83, L0 equals 0.123, and then some of the equations that would go into calculating the computational model of the object. Here is the model, and it takes very slow. But as you can see, the model predicts the motion of the mass as it is oscillating around in an elliptical pattern as it did in the original model. Here are the compared graphs. As you can see, the x position is slightly different, most likely due to dissipating energy due to the surrounding that the computational model didn't predict. And the y model is just slightly set off from the actual model. And what does this mean? Is the energy principle satisfied? Yes, the energy principle is satisfied. As you can see, the net energy of the object right here stays constantly 0, thus we know that it is conserved. And due to and we were supposed to find the oscillation periods using the x and y position data, and in both models you can see that it was 1.52, roughly 1.52 seconds was the oscillation period.